policy. That's good. Now, this we all know. The problem is if we want to evaluate generalist policies that are supposed to do many things, many tasks, many scenes, potentially even many embodiments, all of these things get worse, right? Because now we need to not only evaluate in one task, in one environment, but across many. And so as we want to develop more and more generalist policies, one problem that we're constantly faced is that we need more scalable ways to evaluate these policies. And that's what I want to talk about today. And really what I have experienced over multiple projects that I've done in this direction is that the main bottleneck, in my opinion, for progress in this direction is the evaluation side. And that's for two reasons. On the one hand, evaluation can bottleneck our own research iteration. Like, I work at physical intelligence, we try to train many models, but then actually to be able to tell whether or not we improved those models is a big evaluation challenge. So it bottlenecks us on the research iteration side. It also bottlenecks us as a community. Right? It's very hard for us to tell whether a new generalist policy is better than the last generalist policy. We have a whole section on VLA models in this conference, but very few of these papers actually try to compare on similar things, and certainly not on real-world similar things. So taking all of this together, I think evaluation is one of the biggest bottlenecks that we're facing for this direction of generalist robot research. And so for this reason, over the last year or so, we have done multiple projects where we try to address this evaluation bottleneck from different directions. And I want to give a brief overview in the time I have today for some of the tools that we have built that help us, but hopefully also help you evaluate your policies. And so, like I talked about how all of this is challenging and bad, and we need to work on this bottleneck, but I also want to emphasize that generalist policies really kind of form an opportunity for evaluation at the same time, because with the generalist policy paradigm, we have also seen a bit of a shift, at least in parts of the robotics community, towards a point where it's easier to actually benchmark and compare, right? Because now people actually start training on the same data, which didn't used to be the case in robotics. So we have shared data sets in the community that people have agreed on. And with those data sets, we also have shared hardware platforms, right? There is now multiple labs that have each of these hardware platforms assembled. And so it's much easier in some sense to actually compare on a fair basis different approaches to learning. Okay, so eval is a big challenge, but there's also a big opportunity in the generalist policy direction. Now, unfortunately, in today's talk, I will not present you a single silver bullet on how to solve the evaluation problem. I think there's a bit of a trade-off that we need to cope with. And that trade-off basically lies somewhere on this frontier, but that trades off between the scalability of an approach and kind of the quality or signal-to-noise ratio that this approach can deliver in terms of estimating the policy's performance. And so in today's talk, I want to talk about 3 different approaches that I think lie on different points of this frontier that we have developed over the last year or so on trying to approach the eval problem. So I'll talk about simulated evals, automated evals, and then crowdsourced evals. Cool. Before we can dive into individual approaches, I think we need to take a moment to actually define how we will measure whether a new approach that we propose for evaluation is actually a good approach. And generally, the formalism that we came up with is that we assume that we're given a set of policies, n of them. They're typically generalist policies in my case, but they don't need to be. And then for the purpose of designing a new eval mechanism, we need to assume that we have some sort of ground truth eval score for those policies, typically evaluated by a human. And then what we want to come up with is a method that allows us to estimate that score, ideally precise, but importantly scalable. And so metrics for such approaches may involve just looking at the correlation between those estimated and ground truth eval scores. So we can just look at Pearson correlation. But there are situations where correlation isn't enough. For example, we can see that there are situations where policies are correctly ranked, but not in a linear relation between ground truth and evaluated scores. But in these cases, we may still be happy, right? Like as long as we get a progress improvement signal, that may still be a quite good evaluation approach for all practical purposes. And so in order to capture such situations where raw correlation isn't quite indicative, we came up with the second metric that captures more a ranking notion called mean maximum rank violation, where essentially we look at the worst case violation in ranking that our approach does for the policies in our set. Okay. Just a bit of formalism. It's not super crucial that you followed all of it, but essentially we introduced a few metrics in a paper called Simpler that's here cited at the bottom, for trying to estimate whether a new scalable approach to evaluation is actually going to be a helpful approach. All right. With that out of the way, I want to talk about these three approaches that I mentioned, starting with simulated evaluation. And I think the idea here is fairly intuitive, where the hard part about evaluation in robotics is the real world. So if we can get rid of the real world, then all of our problems would be solved. Now, clearly, this is, that's why I talked about quality to scalability trade-off. Not the final solution, but this is an approach that we explored, where essentially we took real-world environments that we had used in prior projects for evaluating some of our policies. This is an environment at Google. And we essentially sat down and we tried to build simulators that come close, that are essentially visually and from the physics perspective fairly close to those real-world environments, so that we could take real policies and run them in the physics simulator, and then hopefully get scores for those policies that are indicative of their real-world performance. And obviously, if we do that, we will get evaluation recipe that's scalable, that's reproducible and cheap, because it's in simulation. Now, in practice, we tested this across a bunch of different policies that at the time existed in the community, some of my own prior work and others. We tested it across a bunch of different tasks, so the Google task that I had shown before. And importantly, what we typically find in robotics, and this is a fairly general rule, is that standard machine learning metrics, like validation MSE, which people typically use to test whether a policy or whether a model works or not, don't actually correlate well with ground truth robot performance. You can see that the Pearson correlation of validation MSE is really, really low. Sometimes you even find that it's inverted. So that's not a great metric, and this is why basically we need to develop metrics like the simulation evaluation that we did here to actually try and improve over those. Okay, so what matters in those simulate evaluations? We basically had a few versions of that simulator, one that looked very much like a simulator and not like the real world. We then improved on the visual realism. We tried to improve on the physics. What we found in our evaluations is that mainly the visual realism is what makes or breaks a good simulated evaluation for those particular policies that we tested. Whereas in these kind of simpler pick-place tasks that we tested in this work, the physics weren't actually a big problem. Essentially, as long as you model an object and it doesn't fly away once you touch it, usually the physics for those tasks aren't a big issue, but the visual realism is really what can throw off a policy that you want to deploy zero shot. Okay. We built a bunch of these environments. As I had mentioned, we released this as a tool, and people have started using this for evaluation. Now, I don't want to claim that this is, this is the final solution on simulated evaluation. I think there's many ways in which these environments are still limited. We found in follow-up work that essentially for newer policies, the correlation sometimes holds and sometimes doesn't. I think there's details in how these policies are trained that may influence correlation. There's also some tasks for which simulated evaluation is just very hard. Right? So these are some of the newer tasks that we train policies on, and it's very hard to imagine that you can build a simulator for a task that involves such a complicated kind of cloth folding interaction. And so this is why essentially I mentioned that there's a trade-off between the fidelity and the scalability of approaches, and just simulation by itself will not be sufficient to actually solve all of our evaluation problems. So the second project that we explored in this direction is to try to go back to the real world. Essentially bite the bullet of doing real-world evaluations, but trying to think a little bit about what is it actually that makes real-world evaluation costly. And there's really two maybe key things that cost money when you run real-world evaluations. On the one hand, it's the hardware that you need to run those evaluations and the space and so on. But really what it mostly is human effort, right? There's like grad students who need to run these evals. They have limited time. They want to do research, not evals. And so the problem we try to address in this project is that we try to make the human effort part cheaper so as to make our evaluations more scalable. And concretely, what we tried as a solution in this work is to have policies essentially evaluate themselves. So this is what we call automated evaluation, or auto-eval. It's a project led by Paul, who is a PhD student at Berkeley. And yeah, the idea is basically simple. We take cheap robot hardware. We build these, we call them evaluation cells, which are essentially environments that have tasks that these policies may be able to perform. And then we essentially instrument them to a degree where the evaluation can more or less run itself. So concretely, the way this works is that when a new policy gets evaluated, we run the policy. This is a fairly simple open drawer task. Then we run a learned classifier that tells us whether or not that policy was successful. In this case, it was. And then finally, and this is where the policies evaluate themselves, essentially we execute a reset policy that resets the scene to some initial condition that's valid, and then you can loop the whole process. Okay, and we can set that up for various different tasks, and then test essentially whether this type of real-world evaluation still correlates well with the ground-truth human-run evaluation across these different tasks. And we tested a few tasks that are harder to simulate, which is why the simpler correlation isn't particularly strong, but the auto evaluation does seem to correlate well with the human run evaluation. Now, we tested this across longer periods of time, where humans were ideally not intervening much. Over a 24-hour period that we ran these evaluation cells, essentially only 3 times did Paul need to run and fix something, for example, if an object drops. And we also found that there are some hardware limitations, where essentially if you run the hardware continuously for such a long time, you can see deterioration. And so we need to make some stops in the middle to try and have the hardware cool down. But generally speaking, we found that this approach does work well on certain tasks, but it comes with a cost. So here we show basically that this is an open source tool. So essentially you can take some of your policies that you have trained, in this case on the bridge data set, and actually submit them to our evaluation platform. And then within a few hours, you can watch the live stream of what's going on, and within a few hours, you will get back a report like this that essentially tells you how your evaluation went. Okay, so this works really well for tasks that we have automated, but the obvious downside of this approach is that essentially we need to spend a lot of time actually automating tasks. And this is maybe for me one of the learnings of this project, that while we thought it's kind of relatively easy to train these classifiers and reset policies because we can just fine-tune existing generalist policies for that, it turns out that it's actually really, really hard to catch the long tail of issues that you end up with if you really want to get the human to not intervene much. So we spend many, many weeks and iterations of trying to run policies for hours and hours to find all of the issues that these policies may come up with and all the ways in which they may mess up the scene that then requires human intervention. So I would say that this project was a bit of a prototype, but maybe also showed us kind of the limits of where we can get automated real-world evaluations to, at least with today's models. And so in that third part of the talk, I want to kind of talk about an alternative approach where, again, we try to do real-world evaluation, but really try to address that missing piece of how can we get diverse real-world evaluations going in a way that is more scalable. And we had a little bit of experience with this. So this is a project that actually was presented here at RSS called FAST, where we trained a generalist policy that could actually be run on a new robot platform out of the box. So this is trained on the open source Droid dataset. It's a single checkpoint, and you can evaluate it on many different robots in many different scenes. And so because at Berkeley we only have one robot and just a handful of scenes, in order to evaluate this policy and show its generality, what we did in this project is that we sent it to many of our friends, essentially collaborators, who also have this robot platform. And we asked them to evaluate it, essentially task it with some task in natural language, and then test whether the policy can do it. And clearly, compared to something like auto-eval, this way of running eval is much more diverse, right? You get a much broader set of tasks and scenes that you evaluate your policy in. But it's also very hard to scale. Essentially, across many scenes, keeping the initial conditions consistent for a benchmarking effort is roughly impossible. Centralizing such an eval, essentially all putting them into one room and then keeping it there is also really hard, certainly within academic constraints. And so we tried to come up with a solution that would allow us to run such diverse evaluation, but in a way that doesn't require us to keep initial conditions consistent or centralizing the eval. And so this is this final idea that I want to discuss today, which is the idea of running decentralized but locally consistent evaluations. And this is this crowdsourced evaluation point on the top left of this trade-off curve. So the core idea in this project, which we call RoboArena, is that we have a pool of generalist policies that we want to evaluate. And then the way that we will evaluate these policies is that at any given time, we will send 2 of them to one of our collaborators, wherever in the world they are, and they will try to evaluate this policy pair. And now, crucially, for them, they can pick whatever task and whatever scene they want, as long as they run both of these policies back to back. Okay, so it's a pairwise comparison. And then in the end, they provide us a preference feedback, essentially which of these two policies perform better. And the only assumption that we make is that in this pair, they keep things consistent. So they try to initialize back to the same position, don't change the camera angle and the lighting and so on. But importantly, they only need to keep it consistent in this pair, so within like a 5-minute horizon. But then for anything beyond that pair, they can essentially freely choose to change the scene. And we can run this in many different robots, in many different labs, just as we had evaluated our previous model. And then we can aggregate many of these pairwise comparisons into a global policy ranking. Okay, and if you basically keep each pairwise comparison consistent and you have different policies evaluated against each other in different conditions, you can end up with a valid global ranking of all of those policies. Kind of like we rank chess players who don't need to all play against each other at the same time, but they can play locally consistent games, and then we can combine them into a global score. Okay. Now, with this approach, again, we are able to evaluate across a much broader distribution of scenes and tasks. This includes things like diverse clutter situations, many viewpoints, lighting conditions, distractors, deformables, and so on and so on. Basically, we can put these policies really through quite a comprehensive test. And then in the end, we can see that this method actually is able to rank policies quite consistently. So what we show in this graph is that we compared the evaluation that we used to run for droid policies. This is the gray bar here, which is an evaluation run only at Berkeley. So this is basically what we can do within the capacity of one research lab. We have a few different tasks, a few different scenes, but not very comprehensive. And then we compare ranking accuracy to an exhaustive eval. This is basically a thing that we ran for the purpose of this paper, where we asked evaluators to virtually evaluate all policies and all scenes. And as a result, we kind of get the ground truth, and we can see that our pairwise comparison, we tried different ranking approaches, but basically all the right bars, our approach does approach the ranking of this ground truth evaluation quite accurately. Okay, it does also converge reasonably fast, so within a few hundred pairwise evaluations, we were able to order the set of policies correctly. I need to wrap up, I think. I want to encourage you guys to check out this project. I think it's a great way of trying to evaluate policies at scale. We have leaderboards, and we have videos, and we have summaries of how the policies perform on our website. We also have all the resources to get you started. I mentioned, there's open source data sets, there's open source hardware platforms that you can use today. And so I hope this is a really easy way for people to try and train generalist policies and then also evaluate them quite comprehensively and fairly. Cool. With that, I want to close. I hope that I could very briefly, admittedly only, cover each of these works that we have done on evaluation tools for the community. I have one final slide where I try to summarize kind of the pros and cons, because I mentioned it's all a bit of a trade-off. So SimEval is basically high throughput, but there are some concerns with sim to real gap, and also some tasks are plain hard to simulate. The automated eval gets away with tasks that are hard to simulate because you run them in the real world, but it's hard to scale the number of tasks that you evaluate because it's hard to build them. And finally, the crowdsourced eval, I think, is really nice because it gives us diverse tasks and scenes, which we didn't really have before for evaluation. But the throughput, because it's human-run real-world evaluation, it's not a very high throughput tool. Like, you wouldn't use this tool for your ablation studies, for example. So I think this is basically where the trade-off lies in today's tools, and I hope that more research can be done to try to mitigate this trade-off and find a really good tool that everybody can use. All right, with that, I hope I'm on time, and we have some minutes to take some questions.
Questions, Karl?
Ooh.
Thanks for the great talk. I want to know what's your opinion on the idea of training world model as an evaluation tool.
Yeah, so the question maybe for the people online is whether we can use world models as a way to do scalable evaluation. I think it's great. So it's basically kind of like SimEval. It has maybe similar trade-offs where your model may not be perfectly accurate, so there's only an imperfect correlation to the actual real-world result. But it may be more scalable to things like cloth folding, which are hard to simulate classically. This is my mental model. It's basically a learned simulator. This is where it can get to. I don't think that we are there today. I think most video models trained today are not physically accurate enough to actually be used as evaluators. One very common failure mode is that we typically only train them on demonstration data because that's the data that we collect. But then, in your evaluations, you really care about what happens if you're not perfectly demonstrating the right actions. But then in practice, if you look at some of these videos, when the robot tries to grasp an object and the policy misses, once it closes the gripper, the object teleports into it. Because in all of the data you trained on, whenever the gripper is closed, there's an object in it. And so these kind of things make it then hard to use video predictive models as evaluation tools right now. I think there's one successful case that I know of in the literature, which is the Unisim paper, where I think they did 2D pushing evaluation in a learned simulator. But I think there the data coverage was extreme. It was like 500,000 demonstrations on a 2D tabletop. And so then it can work, but I think for the general manipulation case right now, it's still a little bit questionable.
Thank you.
Regarding the crowdsourcing effort, it's great, noble, but I'm a little bit not optimistic, right, in terms of long-term sustainability. There have been crowdsourcing efforts for kind of science in the past. There have been actually less requirements of effort from the people to participate, like just provide perhaps compute for solving protein folding.
Yeah.
And there's a lot of excitement in the beginning, and then they kind of die down, especially when the main novel developers kind of move on.
Yeah. So I'm a little bit maybe more optimistic than I need to be, I guess. I think in the robotics community over the last few years we have seen quite a bit of success of community-wide efforts, right, in the data direction and the model building direction. Now clearly this is kind of the hardest to scale effort because nobody loves to run eval, right? Like in the data direction, you share data and that's it. But here you need to actually consistently run evaluation. I think the only way in which this can succeed is if the community needs it enough, right? Like if people agree enough that we need to have ways to compare our policies to make progress as a community, then this thing can sustain itself. Because we have a system where we kind of control supply and demand, where essentially if you want to have your policies evaluated, you need to evaluate policies for others. So there's a bit of a credit system. And that can essentially, if enough people need evaluations for their papers and they need their policies evaluated, they will evaluate other people's policies. And it's all decentralized, so if one student graduates or something like this, the system can sustain itself. Or if one robot breaks, the system doesn't shut down. So in my mind, it's a little bit more resilient and scalable than prior eval approaches in robotics. But it's maybe, but I agree, basically. I think it's to be seen whether it is enough in demand that people would actually sustain it. It doesn't hurt trying, and I think we're trying hard to convince people to submit, and I think it's a great tool, but it is to be seen whether it will sustain for longer, yeah.
Karl, do you have time for one more question?
The obvious-ish alternative to this in a similar vein would be some sort of centralized, everybody puts in some bucket of money and their job is evaluation. They know that, that's what they do, they become experts at it. Everybody, asks for time on the system. It's credits by dollars instead of credits by credits. Yeah. Is that practical? Is that something we could converge on?
Yeah, I think it's certainly an option. We would need to figure out who wants to do it. I'm not sure whether any academic incentive is set up in a way that somebody would be willing to do this. There may be a way to have industry folks pitch in for something like this, if the incentives are set right, or like the Hugging Face folks, for example, could do something like this. One issue that kind of appears with this is that it's a fairly static setup. Like you need to decide for a certain hardware platform. You probably need to decide for a certain set of tasks that you set up in your evaluation center. And so if somebody doesn't agree with that, like they don't like that hardware platform or they don't like that particular set of tasks that you chose, then maybe it's harder for them to participate. In this distributed eval setup, it's a little bit more flexible. Essentially, some new hardware platform comes up, we just add it to the eval pool. If somebody doesn't like a certain task, it will slowly fade out of the evaluation and kind of the distribution of tasks will stay at the frontier of what the models are able to do. So there have been prior efforts, I think at MPI, for example, there has been an effort on the kind of tri-finger hands, which was more centralized, right? You could SSH into the hand and you could run your policies. But then the downside is that if you don't like tri-finger hands or this particular task or this particular RL setup, then you wouldn't really participate. And so I think there's a bit of a trade-off in how centralized you make it versus how flexible it is.
Yeah.
But I wouldn't want, like, I think it's a good idea, right? Like maybe there should be a grant or something for exactly that.
The mental model I have is places like CERN, but those are I don't know how many billions of dollars facilities those were with government support, like a huge investment that has benefited that community enormously, but that requires so much commitment. Like that's, as opposed to, I'm not talking $1 million type of budget here. Like, I don't know if we could get there, but where you have, because it's so big, you get coverage. They're tasked with constantly doing new tasks, new scenes, etc.
Yeah, I think it could be interesting. The academic landscape isn't quite made for it, maybe in some way, but it may also not be exactly made for crowdsourcing evals across many different labs. So I think
really quickly, one final question.
Yeah, thank you, Karl. Nice presentation. I want to ask, like, out of the three approaches you're talking about today, right? Like, do you see big companies like, say, Pi converging to one of them eventually?
So I kind of tried to make clear that I don't think any single one of them is perfect. I think we very much will need all of these. Like if you look at autonomous driving, right? Like what they do is actually a staggered approach, where first you have a sim eval. If it does reasonable in sim eval, then you bring it into a test phase with a test driver, and then you roll it out onto real.
Honestly, like which one do you think has the best opportunity of helping a company like Pi, right? Like try evaluate checkpoints every day, evolve really fast, right? Like which of the approaches do you think will have that?
Yeah, I mean, if I were to put all my money on one, I would say video models. But for now, I think maybe SimEval would be really helpful. It's also really nice for the community because people can easily share evaluations. They're more comparable than the real-world crowdsourced stuff. But they have lots of limitations. I think anybody who has tried to make SimEval informative has felt the pain of making them work well. But I think, I think that would be a real help. I'm trying to encourage all the big companies to try and build good sim evals for the community. I think that would be really nice.
All right, thank our speaker.